My name's Nick Facey. I'm the Senior Program Manager at Unity Accelerate Solutions.
My name is Jack Sue. I'm a Senior Manager at Boeing Vancouver.
So Jack, we got to do an incredible project together working on AR for inspection on large objects. Do you want to give us a high-level overview from your perspective, what the project was, what technologies we used, and what problems we ran into?
Augmented reality for aircraft inspection was a project around looking at the emerging technology of augmented reality to make the aircraft inspection process more efficient for the mechanic and engineer. Aircraft inspection is something that happens many, many times through the life of an aircraft. And so our thinking was that if we can use paint, augmented dots indicating locations of defects, dents and buckles on top of the aircraft, that would allow the mechanic to see existing damage much more easily and also allow them to identify new damage much quicker. And so we were taking a machine learning approach to anchoring that 3D virtual model on top of the aircraft that they see through the AR device. And what we found in the course of the project is that to train a machine learning model required a lot more data than you could gather, a lot more images than you can gather by just going and taking photographs of the aircraft. And instead, we came up with using synthetic data to generate those images for training of that machine learning model.
How were they currently doing the job? What was the process of the existing inspections?
Say an aircraft is at a gate, and there's a sort of a cursory inspection that occurs at a gate. So a mechanic may walk around with some paper, which he can note and annotate where a new defect might have occurred. There may also be a listing of existing defects. So all defects, bird strikes, lightning strikes, those types of things, what's called dents and buckles sometimes, are recorded in a database. And so the inspector may print out all the existing defects. Now, depending on the type of inspection, like an inspection at a gate is very cursory, as I said, and so the mechanic may spend a lot of time being much more carefully kind of walking around the aircraft, looking at it. They may actually get on cranes and this type of thing to look at the top of the aircraft for damage there underneath the aircraft. In more modern airlines that are using more modern technology like iPads, they could run an application. Boeing actually has an application called Turn Time that basically supports this process. And so, again, it would be typically with paper or maybe with an iPad application that they would carry around with.
We started with, the real world pictures of the plane that we were taking, or, the project team was taking. Mm-hmm. And then we realized we were going to run into a problem of not enough data to train the machine learning with.
Yeah, that's right. We were taking a machine learning model approach to solving that anchoring problem. We went out to an airfield and took thousands of images of an aircraft and also used a particular algorithm to calculate the position of the camera relative to the aircraft. We took those thousands of images, we fed them into the machine learning algorithm and got it to learn how to calculate position based on an image that was coming from the camera. But when we actually went out to the field again after we trained the model and tested it, it didn't do a very good job. And after a lot of analysis by our partners at Simon Fraser University, they determined that the reason it wasn't doing a very good job was that there just wasn't enough data. We didn't need thousands of images. We needed hundreds of thousands of images at a lot of variation in viewpoint. And also, the algorithm is also using the sky and also the background and the markings on the aircraft to do that pose estimation. And so we needed variation in those as well. Variation in the markings of the aircraft, in the background, in the types of, tarmac that the plane was sitting on, whether it's indoors or outdoors. All of those things need to be varied in terms of the image that was used to train the algorithm. And we just couldn't do that with field data. Like we couldn't create that variation, and we couldn't create enough images. It's very time-consuming process to actually collect those images and determine the position, the XYZ position of the camera to really make it an operational process.
And in terms of the next steps towards the solution, because we didn't stop there. So what do we do next?
So after realizing that that's what we need to do is we need to collect a lot more images and a lot more images with variation. We thought, hey, we should use synthetic data because synthetic data is where you create these images using a gaming engine like Unity's gaming engine, like creating realistic synthetic images, which basically act as a proxy for real images you collect in the field, and feed that into the machine learning algorithm. Because you're creating synthetic images in a virtual world, it means you can create millions of images, and very quickly compared to going out to the field and actually taking pictures. And so that's why we came to you guys to talk about if you had the ability to do that at Unity. And it turns out, luckily, that you did.
That's where we engaged the perception team, and we started to iterate on the exact items that you talked about.
Yeah, it was great actually, because we found out through you, Nick, that there's a team at Unity that has been working on exactly this problem, creating synthetic images using the graphics engine, and taking those images and feeding them into the machine learning model. And so what your team was able to do was create within Unity and the perception toolkit the ability to randomize the delivery or the markings on the aircraft. You actually created environments to place the virtual aircraft into, like inside a hangar, different types of hangars, in outdoors, in cloudy conditions, in sunny conditions, with different tarmacs, different ground covering, and different lighting conditions. So sun at a particular position, a different type of light inside the hangar, and also at hundreds of thousands of different viewpoints. That the camera could be above the aircraft, below the aircraft, where on the side of the aircraft, left side, right side, behind the tail, and all sorts of randomized kinds of environment conditions and markings of the aircraft, and take millions of pictures of the environment. And then what we did is we took those synthetic images and we fed them into the machine learning algorithm to see what the impact is. And the results were very promising.
So do you think it'd be safe to say, like, the synthetic images is going to make the possibility of AR for inspection of these large aircraft, like, actually more reality, is moving that bar forward?
Absolutely. I don't think it's possible without the use of synthetic images. I think that synthetics really has made it a possibility to do this type of work. I think that without synthetics, it would not have been possible. That was one of our big lessons learned from the project.
Aside from time, one of the big advantages of synthetic data is rather drastic reduction in cost to generate all the images.
Yeah, absolutely. It's a huge decrease in cost. I mean, it spent SFU and Boeing. And some of our guys went out to the field, and it took them something like 7 or 8 hours to collect something like 3,000 images of the real aircraft. Once the programming is done with Unity and the perception toolkit, it would take like 3 hours to generate 100,000 images, and potentially more, and of better quality in some ways, right? And with more accuracy. And so there's really no comparison in terms of cost.
So aside from inspection, is there somewhere else you think you can see synthetic data going as a problem solver?
Yeah, absolutely. I think wherever there is a requirement for data to drive machine learning, there's a role for synthetics. And that happens in many areas. One example is in aviation. One of the other things that different groups in Boeing have been trying to look at is using machine learning to recognize a defect. And so, for example, if you had an iPad camera or even a drone that's flying around an aircraft and sort of doing surveys of the aircraft, you want to be able to automatically detect, oh, there's something here. There is a dent or a buckle here at this location. So you're giving it a bunch of images of the aircraft, and you're getting the algorithm to recognize this is the lightning strike. This is the bird strike. And in order to do that work, once again, with a machine learning algorithm, you have to feed it many, many images of bird strikes or lightning strikes in order for the algorithm to recognize that this is what they're seeing. And so this is where I see another opportunity that's similar.
If we move away from synthetic data, what about kind of the real-time 3D engine? You mentioned the realism being important. What other use cases do you think you can see in the aerospace industry there?
Aerospace is getting, especially in our area and the things we're involved in, Boeing, 3D models are becoming more and more important. And so people are starting to really realize the value of being able to see planes and components and parts in 3D. I mean, it's being used today, I'm sure, as people know, in the design of aircraft, in lots of areas in the design, right, in the design process. But even within the post-sale market, the services market afterwards, 3D models just enable so many things, allows the end user to visualize parts, to find location of parts. In the future, we envision it to see underneath the skin of the aircraft. The ability to stream a 3D sort of graphics in a very performance efficient way is something that we're very interested in talking about and thinking about and developing applications for.
What was it like to work with the Unity team, the Accelerated Solutions team, the Perception team, Unity as a whole?
It was fantastic. I have to say, it's one of the best partnerships I've been involved in my career. I thought it was just fantastic how, about 3/4 of the way through the project, 2/3 of the way through the project, we decided, hey, we got to take a look at synthetic data. And that ball was kind of picked up by you, Nick, and the Unity team, and say, hey, I think we can help with that. I found that you guys are just super responsive. You put a team on this really quickly. You knew what we wanted to do, and you just got to work. And I was really pleased with how quickly your team was able to build the environments, to brainstorm with us on the best way to get this done. And so I thought it was a great team effort. But I was really pleased what Unity brought to the table.
Awesome, Jack. And that was absolutely mutual on our side. Awesome to work with Boeing. Awesome to work with SFU. Even though we're all three very different companies, it felt like we were very aligned on wanting to solve this problem together.